Hey everyone, and welcome to this video on an introduction to springs. So we'll start by just defining what a spring is and getting a visual. So a spring is just an object that applies a force on that object when the spring is stretched or compressed. It has a natural length that's defined as the length the spring is while unstretched and uncompressed, and it always wants to return back to this natural length. When we stretch a spring, the spring will pull on an object, and when we compress a spring, the spring will push on an object. So one of the properties that each spring has that's unique to that spring is something called the spring constant. And it's a rate telling us how much force we're going to get for a given stretch or compressed distance. So for an example, if the spring constant K was 10 newtons per meter, what that tells us is that we're going to get 10 newtons of force for every 1 meter that we stretch or compress the spring. And so the spring constant is a property of the spring itself, and it depends on what the spring is made of. So is it made of iron or steel or copper or nickel or something, maybe plastic. And it's also how tightly the coils are wound in that material. The units for the constant are going to be newtons per meter, or N/m. So to introduce the equation, the spring force is equal to the negative K times delta x. So the spring force is equal to the coefficient multiplied by the displacement of the spring. The negative sign is indicating that whatever direction you displace it, the spring force is going to point opposite of that direction, which aligns nicely with our definition where if we pull a spring, then the displacement might be positive. Therefore, the force is going to be negative, so it's going to point in the opposite direction. And vice versa for if we compress a spring, then the force is going to push instead of pull. So if we take the magnitude of the spring force and the magnitude of the displacement, the spring compression distance, and we graph them, we'll see that they have a linear relationship. Looking down here, we have the equation for a line y equals mx plus b. The spring force equation fits nicely if we just look at the magnitude. So the magnitude of the spring force is equal to K times delta x. Since there is no other term here, the b value or the intercept value should be 0, meaning the graph should start at the origin. So essentially what we're saying here is if we graph the spring force or the magnitude of the spring force against the magnitude of the spring displacement, we should get a linear graph, and the slope of that linear graph should tell us the spring constant of that spring. So looking here, we have a green graph that has a steeper slope, and therefore it has a higher spring constant compared to the white graph. So something to note here about the spring force is since the magnitude of the spring force actually depends on the displacement, how far we stretch or compress the spring, that means that the acceleration also depends on the displacement. And therefore, we're getting different acceleration values as a spring compresses or decompresses or stretches or de-stretches, meaning we can't use our UAM equations when we're looking at objects that are accelerated by springs. So if we launch an object with a spring, the 4 kinematics UAM equations won't actually work. We will revisit this and get tools to analyze it, but that'll be later on in the course. And that's it on this introduction to springs. Thanks for tuning in, and I look forward to seeing you next time.